Okay, this recording is going to deal with what happens in an elevator, and then we have another example that deals with another situation, another application of Newton's laws of motion. Now, the elevator problem is a classic problem. It has some interesting implications, interesting conceptual implications, and that's why we are doing it. So what we have here, we have a beautiful cat woman standing on top of a bathroom scale. And the bathroom scale is giving us a reading here. It reads 500 newtons. Now, in this case, we are not in an elevator yet. She's just, the bathroom scale is on the floor and she's standing on it. The question is, what are the forces acting on this cat woman as she's standing on the bathroom scale? Obviously, the forces acting on her is the gravitational pull of the Earth, Fg for gravity, Earth on Catwoman, so I'll write it as W, Fe on W, and then the bathroom scale is going to hold her up with a normal force, so Fn of scale on a woman. And both of these forces have to be balanced, since we don't see the woman either flying off or sinking into the bathroom scale. So these two forces in this case are equal to each other in magnitude, or they balance each other out. They're equal and opposite. But remember, they are not action-reaction pairs. They both act on the same object, the cat woman. Now, what if the woman, instead of standing on the bathroom scale on the floor, if that bathroom scale is in the middle of an elevator, but an elevator at rest, a standing elevator? Of course, you all know that the situation is not any different. The Earth still exerts on her the gravitational force that's equal to her weight, and then the scale is going to exert on her an equal force in magnitude, that is the normal force that the scale exerts on her feet, holding them up. Now that's the case at rest. Now the question is, what is the mass of the woman? Now we have a reading on the scale. What does the scale read? And this is the key point. This is the key to this problem. What would happen if I push down on the scale with the woman standing on it? You obviously know that the minute I push down on it, the scale is going to give a different reading. Okay, what about if I push down on the woman? You all know it's going to read a different number. What does the scale read? Does it read the gravitational pull on the woman, or does it read the force the woman exerts on the scale through her feet? Obviously, when I push down on her, that does not change the woman's weight. That does not change the gravitational force that the Earth exerts on the woman. What's going to change is the force the woman is going to exert through her feet on the scale. What that tells me is the scale, what the scale reads is actually the magnitude of the force that we exert on it through our feet when we stand on it. In this particular case, since the woman is at rest, since the forces are balanced, the gravitational force acting on the woman is equal to the normal force exerted on the woman. Remember, this gravitational force is the Earth acting on the woman, and this normal force is the scale acting on the woman. And they are equal in magnitude because they are balanced. Now what the scale reads is going to read the reaction to this force. What's the reaction to that force? Is a normal force that the woman exerts on the scale. So the 500 Newton here it reads, it's the normal force that the woman exerts on the scale. If that force is 500 newtons, if we look back, this is also 500 newtons, because action-reaction pairs are equal and opposite, which means this also is 500 newtons. So great. In this particular case, the force that the woman exerts through her feet on the scale is equal to her weight, which is equal to 500 newtons. So then we know that the 500 newtons should be equal to the mass of the woman times g in magnitude. And that gives us the mass of the woman is going to be 500 newtons over 10 meters per second squared. Remember, if I had to use directions, then I'm going to have to use minus here for the 500 newtons and minus here. And that would work as well. Now 500 over 10, that gives us 50 kilograms. So this is a 50 kilogram Catwoman. Okay, wonderful. Now we go next. Now the question is, what type of motion would result inside the elevator when the elevator is accelerating upwards at 2 meters per second squared? Now, what the question is trying to get to here is, if the elevator as a cage is accelerating at 2 meters per second squared, what's the motion of the scale? What's the motion of the Catwoman? Obviously, all of them are accelerating upward at that same acceleration, 2 meters per second squared. That's the key. Now, before going further with this, let's precise something. What does it mean to say the elevator is accelerating upwards at 2 meters per second squared? What does it mean? It can happen two different ways. It can be that the the elevator is speeding up while moving upwards. If it is speeding up while moving upwards, velocity is up, acceleration, same direction up. That's what we have learned before. For something that's speeding up, acceleration and velocity are in the same direction. Okay. Now, the other possibility for an acceleration upward is moving downwards while slowing down. Remember, whenever an object is slowing down, the acceleration is opposite in direction to the velocity. So if it is moving down and it is slowing down, that tells us the acceleration is pointing up. That's what we have here, upward acceleration. So in both cases, even though in terms of what you see as a result of the motion, they look quite different, they both talk of motion with an upward acceleration of 2 meters per second squared. That's what matters. The acceleration in both of these cases is 2 meters per second squared. And again, everything inside the elevator is accelerating at 2 meters per second squared upwards. Now, the next question what is the net force on the woman if the elevator is accelerating upwards at 2 meters per second squared? Now, what Newton's second law of motion tells us, net force is ma. Now, we know the mass of the woman is 50 kilograms, and we have just decided that she's accelerating upwards at 2 meters per second squared. That immediately tells us that the net force acting on her is 100 newtons upwards. Okay? Now, what are the forces acting on the woman while she's accelerating? One thing that we know now, since what we just have calculated, the net force on the woman is not zero anymore. What that means is the forces acting on her are not balanced anymore. Okay? What are the forces acting on her? The gravitational force, F G of Earth on a woman. Is that going to change? Of course not. The gravitational force on the woman is not going to depend on any way the woman is moving. It's always given by FGE woman is going to be mass of the woman times G. And in this case, that's going to be 50 kilograms times 10 meters per second squared. And it's going to be 500 newtons in the downward direction. As long as she stays at the surface of the Earth, that's the gravitational force on her. That's one force. Now, what's the other possible force on her? The only other thing that we see acting on her is the scale exerting a normal force on her. Fn, scale on a woman. Now, what this tells us is FNSW cannot be equal to FGEW anymore, since the forces are not balanced. Since we have a 100 Newton net force in the upward direction. This seems a repeat. Okay, actually, what is the normal force on the woman when the elevator is accelerating upward at 2 meters per second squared? Okay, to find the normal force, we try to write down our Newton's second law of motion. What does it say? The sum of all forces is equal to the net force. We have decided that our forces are going to be the gravitational force that the Earth exerts on the woman, plus the normal force that the scale exerts on the woman, and we said that's going to be equal to our net force, and we said that's equal to 100 newtons upwards. The gravitational force the Earth exerts on the woman, we said it's 500 newtons downwards, so that's going to be minus 500 newtons, plus FNSW is going to be equal to 100 newtons. So if we solve for the normal force, that gives us 100, and I move the minus 500 to the other side, so it becomes 600 newtons. Upwards, it's positive. So the normal force that the scale now exerts on the woman is not 500 newtons anymore, it is 600 newtons. Now the next question is, what does the scale read when the elevator is accelerating upward at 2 meters per second squared? Of course, that's what we discussed earlier. What does the scale read? It reads the value of the normal force that the woman exerts on the scale. And what's that normal force equal to? That normal force is the reaction to the normal force that the scale exerts on the woman, and the normal force that the scale exerts on the woman, we just calculated it as 600 newtons, which means that the woman is going to exert a 600 Newton force on the scale, and the reading is going to read, the scale is going to read 600 newtons. Now the next question, what does the scale read if the elevator is moving at constant velocity? If the scale reads at a constant velocity, that tells us that the net force is equal to 0. The net force on the Catwoman, on the scale, on anything is 0. If the net force is 0, that tells us that the forces are balanced. If the forces are balanced, what does that mean? If the forces are balanced, that means the normal force that the scale exerts on the woman is going to be equal to the gravitational force that the Earth exerts on the woman. And remember, this is going to be equal to the force that the woman exerts through her feet on the scale, which is going to be equal to the reading of the scale. This one, we just established it as 500 newtons, so the scale is going to read for us 500 newtons. The same value as if it were at rest. Now, what if the elevator is accelerating downwards? Before I answer this, again, let me focus on what we said before. We talked about this when we talked about accelerating upwards. When are we going to have an acceleration downwards? Either one of two cases, when the velocity is down and we are speeding up with an acceleration down. Moving downwards and speeding up. Or if we are moving up and slowing down. So the two cases, speeding up while moving down or slowing down while moving up. Both cases result in an acceleration downwards. Now, if my acceleration is downwards, it's the same situation as we had before, except now my net force is going to be 50 kilograms times minus 2 meters per second squared because of the negative direction. So that's going to be minus 100 newtons, which means when I write the sum of my forces, the gravitational force Earth on woman plus the force, normal force of scale on woman is going to be equal to minus 100 newtons in this case. Remember, this is minus 500 newtons. When I move it to the other side, that gives me the normal force that the scale is going to exert on the woman. In this case, it's just 400 newtons. The reading of the scale is going to be equal to this value because the force that the woman is going to exert through her feet on the scale is going to be equal in magnitude to this. So what's the bottom line of this says? It says if the elevator is accelerating upwards, a person inside the elevator is going to provide a higher reading. The scale is going to provide a higher reading than the actual weight. If the elevator is accelerating downwards, the scale is going to give a lower reading than the actual weight. Okay, this case here, accelerating downwards, is much better than any of the weight loss programs probably that you heard of. You can get an immediate lower reading on a scale.